And thanks for joining us for this very last video in the NMR structure elucidation series. I should say that in the videos we kind of only talked about like what you need to know to interpret spectra. Probably the most difficult and time-consuming part of learning this material is putting it all together to actually do a problem where you have to figure out the structure. And so for that reason, I really can't stress this enough. I'm glad you've gotten this far in the video series. Hopefully you're watching this before the class time so that we can actually use all of the class time into on figuring out structure elucidation, figuring out those problems. Okay. Now the last piece of information that or type of interpretation knowledge I want you to have is about carbon C13 NMR. And these are a little bit different than proton NMR that we've been studying, especially in that the normal isotope for carbon is C12. That's the majority, 99% of them. But because they have even number of protons and neutrons, there's no total magnetic, there's no sum magnetic spin for the nucleus. So they're invisible to NMR. That's unfortunate. But C13 isotope is because of the odd number of atomic particles, right? You have there is a magnetic spin that you can observe. Okay, and so now the catch is only about 1% of the carbon atom population is C13. The sun's hitting me. So for that reason, it's like about 100th times less sensitive than proton NMR. Often in practice, you have to acquire for a much longer time on your sample to see to get a useful spectrum. Now, just like we emphasized that the chemical shift table is really important for proton, I can say the same about carbon. If you become really familiar with the proton NMR chemical shift table, like the carbon shift table may look kind of familiar because the distribution of these functional groups are about the same, right? They kind of show up around the same similar areas relative to each other. Now, the major difference is we're dealing with much bigger chemical shift numbers, like tens and hundreds, right? So that's kind of what the second item means, is if you kind of remember the value of like proton on an alcohol or ether carbon, that was around 3 to 4 ppm. That shows up, the carbon shift for that carbon is like maybe about 20 times more than that typically. That's kind of a very rough rule of thumb. There's no rule like that, actual rule like that, okay? Just like with proton, chemical shift table that looks something like this will be given to you for my exam, but not for the ACS final exam, just for you to be aware. Here's a comparison between proton and carbon NMR spectra. At the bottom is proton of this molecule. There's only 2 signals attributed to this structure, right? Now, of course, this carbon doesn't have a proton, so that doesn't show up in the proton NMR, but that can show up in the carbon NMR. Okay, and so there's a total of 3 signals for the carbon NMR. Just like with proton, TMS or tetramethylsilane is used as the reference for 0 ppm. Now, here's another look at like an actual real life carbon NMR, and I really regret that my face is right here right now because you can't see these 4 tall peaks here, or 1, 2, 5. They're about this height in the carbon NMR, and you notice there's like a really tiny peak here, smaller peak, and a like fairly large peak. What's going on? Well, the 5 peaks over here are in the alkane range, and not too surprisingly, they're these 1, 2, 3, 4, 5 carbons. The one tall peak is this peak, partly because there's a symmetry here, so both of these 2 carbons give rise to the same single signal, and so it's a little bit taller than others. This peak is, I should say, this smallest peak here is actually this carbonyl ester peak. And one of the things about carbon NMR is the peak areas are not proportional to how many carbons you've got, because this peak, which is that peak, is accounts for the same number of carbons as like all these peaks that are about this tall over here. Again, sorry that my face is hiding them. And now, if there's more carbons, it's relatively speaking, it's usually taller. Like this medium peak is this carbonyl. It's a little taller than the other carbonyl because it's there's two of them that give rise to the same single peak. But I want you to notice that carbon atoms with no hydrogen on it, like the carbonyl carbons, often have a very small peak, and that's because the protons on a carbon sort of help the carbon to relax better, and so for that reason give a stronger signal. So carbons that do have a protons give a decent signal. Carbons with no protons give a horrible signal. Now, if you're really sharp, you might notice there's a few peaks down here that are really tiny, and that may look like just a small impurities, but they actually come from this fluorinated carbons, which fluorine is NMR positive, as in it's visible on NMR, so you could even do fluorine NMR, but another consequence is they can split other signals. So these are really tiny signals because they don't have protons on them that are split by fluorine. You don't need to know anything about fluorine NMR. Carbon NMR, it's much simpler than proton. The only thing you care about is how many signals do you have, which tells you how many different kinds of carbons you've got in the structure, and then the chemical shift, right? Another small clue that like you shouldn't strictly rely on, but it's a clue nonetheless, is if you see a really small peak, often that means that that is a carbon without a hydrogen on it. And as for that, you don't have to really think about splitting in carbon NMR because C13 is only 1% of the population in molecules, so it's very unlikely that there's going to be two adjacent C13s that can split each other or couple to each other. Now, C13 can couple to protons, so technically you're supposed to see that splitting pattern, but most carbon NMR that we will see, and all carbon NMR we'll see in our class, use what's called C13 proton decoupling, so that all carbon signals show up as singlets, and that's kind of the convention. If they're split, it's just too small to see what's going on anyway. So here's another proton on carbon NMR pair example, right? Aldehyde carbons are fairly big because it does have a hydrogen on it, but notice like carbon like this carbon is really tiny. Often carbon NMR also would show the carbon from the solvent, which is CdCl3, which is split into a triplet because of the deuterium, which has two subatomic particles in it, or one neutron and one proton in the nucleus, and so that shows up usually at 77 ppm, and that's another thing I want you to know. Here's a example of a carbon chemical shift table. Unfortunately, this is from another textbook, but here's the sort of more first upfield half of the spectrum would show either alkanes or alkane type of carbons attached to either alcohols, amines, or halogens show up there. In the downfield region, like sort of 60, 70 ppm and above, you would see double bonds or triple bonds. Benzene typically around 120 something, and then the carbonyls show up in this region. If you have about 200 ppm, that's always either aldehyde or ketones. That's really easy to spot. The last thing we want to talk about in terms of carbon NMR is there's this really useful tool called DEPT experiment, which stands for this. We don't need to know what it stands for, but I do want you to know there's two types of DEPT C13 NMR experiments you could run. One is DEPT90, and then the other is called DEPT135. Technically, there's a thing called DEPT45. We won't talk about that in our class. DEPT90, what's nice about it is only selectively shows you methane carbons. That means carbons with just one proton only, and that's it. DEPT135 gives you methane, methyl CH3s, as well as methylene in actually two different phases, which we'll see what that means in a sec. Why is that useful? Well, because for a couple of things. This will help us kind of count how many protons you've got in your molecule in case you don't know the molecular formula to begin with. But also it helps you with like more information about the carbon, because here's the regular carbon NMR. Just by looking at this, I don't immediately know if this peak belongs to a carbon with 2 hydrogens or 3 hydrogens or 2, what have you. But with DEPT, we can figure that out to give us more clues about the structure. The one advantage for regular carbon as opposed to DEPT is regular carbon NMR can show carbon like this that has no protons on it, but DEPT can't. That's the only sort of limitation. But here's DEPT90 spectrum. Notice there's only 3 carbon signals for this same molecule because it only shows methynes. There's 1, 2, 3 methine carbons or signals that we should see, right? And so we only have 3 signals here, D, E, and F. Now, I'm not really sure why there's a high difference between E and D. Both of these 2 carbons for 1 signal each, because of the symmetry. There's 2 sort of D carbons and there's 2 E carbons. So these should be about the same height, but they're a little different. Stuff like that happens in real life. The examples. F, understandably, is shorter because there's only 1 carbon coming from F. But these are all methynes, which means CHs. Now, DEPT135 is a bit more, we need to look at it in more in depth. That's a pun. Because it shows basically everything except for quaternary carbons, meaning like carbon with no hydrogens. So it shows the methyl and methynes. So here's a methyl group, A, shows up now in addition to E, D, and F. And then also the methylene, the B carbon, which is down here. You notice in DEPT135 there's 2 phases. The positive phase, which is like normal. The negative phase, which is a peak that's going downward. And so on the top positive phase, you would see methyls, CH3s, and methynes, CHs, both. And then in the negative phase, you will see methylenes or CH2. So basically what you do is if you combine DEPT90 and DEPT135 by reasoning, you can deduce which each peak is what type of carbon, right? These 3 showed up in DEPT90 and it shows up in DEPT135. The only thing that should be in common between the 2 are the methynes. So that's how you know for sure these are methynes. And this did not show up in DEPT90, which means this cannot be methine. The only thing it could be is a methyl, right? So that's how we know. And lastly, the peak B here, because it's in the negative phase, you know it's CH2 or methylene. So with that, you get to figure out more information about the structure, but it's also really helpful to figure out how many protons you've got, because you can count methyl groups and methine groups and methylene groups, how many you have. Now, of course, one thing you have to be careful is, of course, the symmetry, right? D actually accounts for 2 carbons or 2 methynes, so it's not just 1 CH, but 2 CHs. So you have to take stuff like that into account. Which you don't always know, because you don't want to make too much out of the height or the size of carbon peaks, but at least the depth gives you more clue, more information. Now, in class, we're going to put all these together to figure out the structures of unknown compounds. See you then.